All right, thanks everyone, and thanks for having me to the center. So my name is Allison Okamura. I'm a faculty member here in the Department of Mechanical Engineering, and I'm going to be telling you about some of the work that we do in my research lab and how it affects some of the issues that have been discussed at this symposium. So my lab is called the Collaborative Haptics and Robotics in Medicine Lab, also known as the CHARM Lab. And if you don't know what the word haptics means, that's fine. We'll find out in a minute. So I'm going to start with a quiz. Actually, so I'm a faculty member. I call everything a quiz. It's actually a poll. There's no right or wrong answer. I want to ask, if you think about the senses that you have in your body, hearing, sight, smell, taste, and touch, if you ask the question, which of these senses is most valuable to you, or maybe I'll ask it another way, which is if your senses were taken away one by one, which is the one that you would relinquish last? Okay? So which one would you give up last? So let's see who votes for hearing. Raise your hand if you vote for hearing. We have one vote for hearing. Two, okay. Sight. Who votes for sight? Sight's usually a big winner when I ask audiences about this, thank you. Smell, a couple, three. Taste, a few for taste. The only group I ever had where it was a majority of taste was a group of automotive engineers from Korea. I don't know why. Maybe it's because the CEO raised his hand first, but that was a crowd pleaser at that particular group. Okay, last, touch. Who votes for touch? If you know what haptics means, you probably know that I'm a touch researcher, and so I appreciate the shout out, although usually sight wins. All right, so of course there's no right or wrong answer here, but the question is, as we think about the interfaces that we have with the world around us, with other people, with our computers, with our environments, both the natural environment and the built environment, what are the senses that we need to invoke? How does this affect people with different health problems? How does this affect people that do or do not have access to technology? I'm very interested in thinking about the sense of touch and the role that my work as an engineer can play in restoring it. So when we think about what would it be like without the sense of touch, and I'll sort of paint this picture for you, for those of you that didn't vote for the sense of touch, it's actually a pretty bleak existence. There's a pretty old BBC documentary you can find online called The Man Who Lost His Body, about a man when he was fairly young who had a disease called sensory neuropathy, and he lost all feeling from his neck down. And if you don't actually have a sense of touch or a feeling of your body's position in space or its interaction with the world around you, not only do things become very dangerous in terms of potentially cutting yourself and not realizing it, but even something as simple as walking becomes very difficult, because the way in which we control our bodies is all this natural feedback that we're used to getting, that if you suddenly don't have it, you don't know where your legs are going or where your feet are touching the ground. Say you're a man like Ian Waterman in this video, you would crumple to the ground unless you made up for that loss of touch with your other senses. For example, looking at your feet as you walk. So he would say, oh, if someone turned off the light, I would fall over, because he didn't have other senses to account for this loss of sense of touch. Now, we are not in a population that is most likely to have something like sensory neuropathy or even a prosthetic limb where you might lose your sense of touch. However, there are a lot of scenarios, both practical and pretty widespread, where we as people lose our sense of touch, and especially as we interact with technologies and try to do new things. So, for example, all this row of pictures on the right here are the first three are different types of teleoperated robots. So if you have a remote robot to accomplish a task that's maybe too dangerous, too small, or too remote for a human to do it, then you need some kind of dexterous robot that can accomplish that task. But the AI is not there yet in many mission-critical situations, such that we cannot expect the robot to do it completely autonomously. So that means you have a human operator in the loop who is driving the robot. But if you're doing a manipulation task where you're interacting with the environment and things are not all cut and dry like they might be in an industrial setting, and you need to react to uncertainty, you need to have that sense of touch as well as some of the other senses in order to have an efficient, appropriate, and safe operation. So one of the areas of interest of myself and my lab, as you can imagine from the title including medicine, is robot-assisted surgery. So that's this second from the bottom one, where you have a teleoperated surgical robot. This is from a company just down in Sunnyvale called Intuitive Surgical that does hundreds of thousands of robot-assisted surgeries per year. And they actually have to do this effectively without haptic or touch feedback to the human operator. So maybe I should back up a bit, and I kind of said this in passing, but haptics means anything having to do with the sense of touch, and we're interested here in haptic technology. So what we do is we work to take systems like this and add that sense of touch back into them in order to help humans operate at their best. But even if you're not a surgeon or an astronaut or someone who's doing demining, you are interacting with technology that has gives you very limited access through all of your senses. So as virtual reality and the metaverse become more popular, we want to have experiences, interact with loved ones, train in simulators. We need to be able to have these experiences be more natural and more like the real world in order for people to adapt to them. So how do we do that? Well, the type of application areas where I'm interested in having these haptic devices or touch-based devices include human-human interactions. Here's an example of maybe a parent interacting with a child who's remote during the COVID-19 pandemic. Of course, this is something that was very valuable to people. How do we connect with our loved ones remotely? There's also connections to different types of technology. For example, agents. My smartwatch here will vibrate if there's directions going on it to tell me when I should turn. But the haptic feedback is so limited, I don't know whether I'm supposed to turn left or turn right. So if we could keep our eyes on the road, or if I'm on a run, if I could keep my other senses focused on what they should be doing, I could use the sense of touch in order to get additional information. And finally, as autonomous or semi-autonomous robotic devices become more ubiquitous in our homes and in our environments, being able to communicate with those devices in a more natural way is important, again, without overloading most people's favorite sense, which is sight, and being able to leave sight for what it is good for and allow people to focus on the task that they need to through vision and using the sense of touch where it's applicable. So let's talk a little bit about what the technology is and what it can and can't do. So when I was a graduate student in the 90s, this is what haptic devices looked like. They were sort of desktop robots that you grasped with your hand. That device was about $30,000, had lots of expensive motors, and it was very heavy. And the whole goal of these types of kinesthetic or force feedback haptic devices is they would push back on your hands. And they were amazing. You could feel these virtual environments, you could feel virtual objects, and they were extremely compelling, but they were expensive, totally not mobile, and they had to be programmed only by experts. So what we're looking at now in this field is trying to move these devices more into something that anyone can use. And our first foray into this was actually creating educational haptic devices. So I think I became a mechanical engineer because I like to learn with my hands. I'm not great in learning from a book or learning from a lecture like this one. I like to touch things and build things. And so there are a lot of haptic learners out there who are like that. And so we developed these low-cost, Lego kind of like 3D printed haptic devices, little kits that move in one direction that let you feel virtual springs, devices that let you move and feel forces in more dimensions, and even devices that could help you learn math through the sense of touch. And all these devices were great, but as you can see, they're still all things that go onto the desktop. It's not something that can move around you and really become a natural way of interacting with the world, even if it helped in these educational applications. So what I want to tell you about now is some examples of technology that we are developing to try to help connect people through cutaneous or skin-based interfaces. So rather than pushing back wholesale on the hands, we now stimulate the skin locally. And the reason why this is a good idea is that it turns out for most of the manipulation that we do in the real world, we are interacting with objects with relatively light forces. And really, our muscles and our joints don't really come into play at all. We're interested in the textures and the local information that we feel only at our fingertips or maybe at the skin on other parts of our body. So what this video here is showing, and you can tell it's from the late 70s, from the attire, but it's a very famous study where they show a woman simply lighting a match, and she can do that task very ably. And then on the other side, you'll see in a minute a video of the same woman performing the same task, but she's had a local anesthetic applied to her skin. She can still see, she can still move, she can still feel forces in her joints and in her muscles, but she just can't feel her skin anymore. And you'll see her try to do this very simple task and struggle mightily. So she has all of her faculties, she's just losing that skin feedback, and she's having a very difficult time coming up to just grasp this simple match, and eventually she'll get her comet match lighted. Okay, takes her a lot longer. And interestingly, you can encounter this yourself as well if you've ever been out in the snow. Sometimes I think I'm speaking to all Californians because I'm a Californian. I'm sure most of you have been out in the snow. And in the snow, in the cold, your tactile sensors embedded in your skin can actually get knocked out. Not permanently, but temporarily. And you fumble with your jacket, you fumble with your buttons and your zippers. And sometimes people think, oh, I'm so cold, I can't move. But it's really not about your lack of ability to move. Rather, it's about your lack of this cutaneous or tactile sensing so that you can no longer understand the contact conditions between your skin and the environment. So with this inspiration and knowledge about all of these amazing sensors that you have embedded in your skin, which I won't go into in detail, we've been developing tactile devices that stimulate the skin. And I'm going to start with a really easy one, which is vibration. So everyone's experienced haptics vibration here likely because your cell phones will vibrate as a non-visual means of alerting you that something's happened. Now that vibration is very simple, and it usually is just there to call your attention so that you will then look at it with your eyes. But nonetheless, it's a useful cue that is private and very salient. It's very noticeable, and unless it vibrates very loudly, the hope is that other people around you wouldn't notice. So vibration feedback, however, can be much more than this event or call to attention. So on the medical side, I want to give the example of passive tactile stimulation. So we've been working with patients who have a loss of motor function after having a stroke. And one of the ways that this presents itself is in spasticity, which will be a seizing of muscles that will disallow movement. So we've developed gloves that provide simple vibrations across different areas of the hand and shown that after having an 8-week intervention of wearing such a haptic device with these vibrations, these patients can score much better than control subjects on a test of mobility. So in this case, a higher score is a good thing, right? So you want a bigger number that will show your improvement and show your recovery, this motor recovery from stroke. So something as simple as a vibration in the hand, now even if you have no idea what the neuroscience behind this is a very compelling thing for patients. So how do we get this technology into the hands of patients, I think is one of our challenges, and one of the things that we need to understand is, and this is the kind of group that can provide feedback about this, is how do you get unusual medical technology that provides simple solutions at a relatively low cost, for example, to more expensive clinic-based rehabilitation technology into the hands of patients. Another type of vibration that is useful is more about conveying information. So I said the vibrations on your cell phone or my watch are really just there to call your visual attention. But the vibrations can be more sophisticated than that. If you code in vibrations that are not simple sinusoids but have interesting shapes to them, like the ones up here, you can provide asymmetrical tugs to the fingers in different directions. So you can't feel it, but I can tell you what the person in this video is feeling. What they're feeling is tugging in certain directions, and there's no net force on the hand, but it's causing them to feel that they should move in a particular direction. And so that means these haptic devices could be used to provide more directional information, more rich and useful pieces of information that can help people navigate their world, whether it's just someone who doesn't want to take their eyes off the road, or it's a blind person who's attempting to navigate. So vibrations are kind of like a cheap person's haptic feedback. We can get more sophisticated. Hopefully not too sophisticated because we don't want to go too expensive. But we've been interested in how do you deform the skin in more static ways to provide useful information. So on the more expensive side of our devices, this is basically a fancy little robot that you put on your fingertip, and as you interact with a virtual environment, it pushes on the skin in 3 different directions: normal to the skin and shear to the skin. And all of this creates an incredibly naturalistic sensation of picking up and manipulating objects. People have a lot of fun with it too. So you pick up these virtual objects. There's nothing that really prevents you from squishing that virtual object, but the haptic feedback you get in your fingertips is so compelling that it causes people to make more the right movements. And if you're imagining you're trying to get people to interact with other people remotely or interact with a virtual environment, that having these smaller, relatively lightweight wearable devices on the fingertips can be an advantage over these old-fashioned, clunky, robot-like devices that sit on your desktop. And we've made all kinds of different versions of these devices. We've been trying to make them lighter and lighter. So we made an origami-based version, which folds instead of having regular joints. And then this one I'll show you in a video is a fully 3D printed haptic device connected to pneumatics for air. And it's, someone said it looks like a large diamond ring. But basically, it's one that you put on your fingertip, and it provides all of those same directions of force at the fingertip. But it's all monolithically 3D printed into one object, and it can provide this compelling feedback when you're interacting with virtual objects. All right, so we're getting our devices lighter, hopefully cheaper. They're on the fingertips, but there are going to be a lot of things you want to do in your life where you do not want things stuck to your fingertips all the time, right? So now we want to know, how do we move these devices off the fingertips and onto other parts of the body? This is a bit challenging because we actually have more haptic or cutaneous receptors in our skin on the hand than we do on the arm and other parts of the body. And also, we're used to exploring the world with our hands and not so much getting feedback that has information in these other locations in the body. So this is a little challenging, but we have been able to show that even with really simple devices, people can interpret, for example, manipulations they do in a virtual environment, even if they're getting the feedback on a different part of the body than the hands that they're using to do that manipulation. But even beyond that, as I mentioned in the beginning, we're interested in using the sense of touch as a way to connect people. Social touch and the realization of its importance has become more to the forefront with COVID-19 and the desire for people to have a physical connection. So what we've looked at is for simple types of haptic interactions that are social in nature. So this is me stroking my husband's arm, which is a common loving gesture, a calming gesture. And there are actually lots of scientific studies to show that this is actually healing for people. It makes them feel good and it actually promotes their health. So how do you do this in a device without literally taking a robot finger and running it down your arm? Well, it turns out you can start to get a little bit tricky with arrays of different actuators, different motors that can actually push in different locations on the body. And if you get the timing wrong, it feels creepy. But if you get it right, it feels really good. And it actually feels continuous and pleasant. So we took this, I'll skip ahead a little bit, a step further. And we thought about what if we actually want to build a social touch display that could communicate some things that people normally communicate through vision, for example, with emojis that you text on your cell phone. So what we did is we recorded people interacting with the sense of touch. So we had people wear a sleeve with sensors in it so that we could record if one person touches another person to say, "I'm so excited I got a new job today." We would be able to record that touch. And then we took those touches and we played them back on a wearable device. And we showed that people could do a great job at recognizing these artificial touches and the way in which they map onto a classic form of human-computer interaction evaluation, which is to look at arousal and valence, where arousal is how excitable you are, and valence is sort of how happy versus sad you are. And these different touch cues, for example, gratitude, attention, happiness, wind up on this chart where you expect kind of good arousal and positive valence. And things like sadness wind up with negative valence and low arousal. So it turns out that these artificial touches can be pretty naturalistic, and people can recognize what they're supposed to mean. So this is exciting because it means that we are going to be able to start using technology to provide these physical connections between humans who are remote, whether it's because of health or just distance, between humans and agents, as well as humans and robots. And with that, I'll thank you for your time. Thank you very much. Yeah, so the question was, what kind of applications are there for disease? And you specifically mentioned Parkinson's. Yeah, well, my lab has been looking at stroke. There's a researcher here at Stanford, Peter Tass, who has been specifically looking at similar vibration devices for Parkinson's, and he's actually had amazing results. Some of the stoppage of motion and restart of motion problems that Parkinson's patients see can actually be stimulated non-invasively using these type of haptic interfaces. There are also applications, like I mentioned, in teleoperated surgery, anything where you need to be operating remotely or at a different scale. So in that case, the feedback comes to the surgeon, not to the patient who's laying on the table. But many medical applications ranging from rehabilitation to surgery and any medical task where a clinician would like to provide remote rehabilitation or remote therapy or even remote diagnosis are good candidates for haptics when haptics is actually relevant to that disease or medical situation. Thanks.
Okay, any other questions? Yes, Tara.
I think your research is just fascinating. I have a question based on the chart that you had of the valence and the emotion part of things. Do you do any research that tries to work backwards, if you're trying to detect sadness, but then reuse maybe some of the other mechanical indicators towards that, instead of just looking at mechanical to emotion?
Yeah, that's a great question. So the way I would interpret that is, what is the role of biofeedback in terms of helping sense, while being able to both sense a scenario and then actually react to it and maybe steer it into a better one. And there are a lot of ways to acquire that biological information. Some of it is through vision, looking at people's facial expressions. You can look at skin galvanic response, like I'm sweating up here a little bit, right? Like giving a talk. And so, being able to sense someone's state through various physiological measurements, that can actually be used to steer the feedback. Interpreting someone's touch automatically is not something that we have done yet, but there are definitely researchers who are looking at that issue. Thank you.
Well, thank you very much.
Okay,
Appreciate
thanks,
it.
everyone.